Hello everyone. Today let us discuss about electric potential. So electric potential is given in NCRT in chapter 2 for 12th standard as well as for state board colleges also. It is a topic in the second chapter of electrostatics. So we will today completely discuss about the electric potential and we will derive the expression for the potential due to a point charge. We will derive the expression for the potential due to a point charge. Before deriving the expression, first let us define what is electric potential. Let's start our discussion. If you can see here, there is a charge capital Q. It is a positive charge. There is a charge capital Q. It is a positive charge. So this is the main charge. Because of this, there is an electric field created. You can see capital Q creates an electrostatic field E bar. And we want to bring another unit positive charge, small q, towards capital Q against the electrostatic repulsive force. So here you can see we have taken a charge capital Q and we have placed it at the origin. Now we imagine that we bring a test charge small q from a point capital R to a point capital P against the repulsive force on it due to the charge capital Q. Why I am saying there is a repulsive force? Because capital Q is a positive charge and small q is also a positive charge. Then, naturally, according to Coulomb's law, there is a force between them, and because they are like charges, they repel each other. So, we are bringing small q towards capital Q against the electrostatic repulsive force. As shown in the figure, you can see capital Q is positive and small q is also positive. Both are positive. As both are positive, they repel each other. There is a repulsive force between them. Now, we are bringing small q into the electric field created by capital Q into the electric field created by capital Q against the repulsive force. That means we are moving it from R to P. We are moving it from R to P. Now, if you see that here, we have to note 2 points. The first one is, the first point we have to remember here is the test charge small q is so small that it does not disturb the original configuration. That is, the charge capital Q at the origin. What I want to tell you here is, just I'll give you an example here. If you take a big magnet and take a small iron piece or a nail and bring it towards the magnet, the nail will be attracted by the magnet. But magnet's position will not change because of a small iron nail. In the same way, in the same way, when small q is approaching capital Q, it should not disturb the configuration of capital Q. It means capital Q should not move from its place. It should be at the origin only. It should be at the origin only. And the second point to be noted, to bring charge small q from R to P, we apply an external force F external, just enough to counter the repulsive force. As per the Coulomb's law, there is a force of repulsion between them. As per the Coulomb's law, there is a force of repulsion between capital Q and small q. We know that. That is equal to 1 by 4 pi epsilon naught capital Q small q by r square, where r is the distance between both the charges. Now, that is the electrostatic repulsive force. That is the electrostatic repulsive force. So, what you have to do now, we have to push small q towards capital Q so that it should be it should be equal to the it means the force should be equal to Coulomb's force, that is Coulomb's repulsive force. Then only we can move small q towards capital Q. That means external force, whatever the force we are applying from outside, it should be equal to the repulsive force. Then only we can move small q towards the capital Q. And if you are bringing small q towards the capital Q, we have seen the 2 points. First, it should not disturb the position of capital Q. Second, the applied external force should be equal and opposite to the repulsive force. These 2 points we have already noted. Now, we are bringing the charge small q with very slow constant speed. So the charge small q is brought with very slow constant speed. In this situation, work done by the external force is the negative of the work done by the electric force and gets fully stored in the form of potential energy of the charge q. So, in simple words, we are applying some external force and bringing it towards the origin. When you are bringing small q towards the capital Q, we are applying some force. That means we are doing some work, because by applying the force, the displacement was there for small q. Therefore, work is done. Then the work is done by this external force. It will be stored in the form of potential energy. In simple words, whatever the work we are doing, whatever the work we are doing to bring small q towards the capital Q, that will be stored in the form of potential energy of the charge small q. So that is what we have to remember. The work done will be stored as potential energy of the charge small q. Now, what is the work done? We all know, even from the 11th standard, work done is equal to force into displacement. Here, the work done in moving the charge small q from R to P, so we have to integrate it. We have to integrate it. That is WRP, that is the work done in bringing the charge small q from R to P is equal to integrate from R to P F external dot dr bar. We know work done is equal to dot product of force and displacement. So F external dot dr bar. But earlier we have seen F external is equal to minus Fe bar. That is negative of electrostatic force. That is opposite of repulsive force. Therefore, that is equal to minus integration R to P Fe bar dot dr bar. Let it be equation number 1. Thus, the potential energy delta U is equal to UP minus UR. UP means potential energy at the point P. UR means potential energy at the point R. That is equal to WRP. WRP means work done by this external force in moving a charge from R to P. Therefore, the conclusion from this picture, what we can say is the potential energy difference is equal to work done. The potential energy difference delta U is equal to WRP, that is equal to work done. So from this equation 2, we can conclude first point, W or P depends only on the initial and final positions of the charge. It is independent of the path taken to go from one point to the other point. The first point we note here is whatever the path it may select, it does not depend upon the path. It depends only on the initial point R and the final point P. You need not go in a straight line, you can go in a curved line, or you can take a curved path from R to P. Whatever may be the path you take, it does not depend, it means work done does not depend on the path you have taken. It depends only on the initial position and the final position. That means it depends upon the position of the point R and point P in this picture. It does not depend what type of path you are selecting. It depends only on the path. It depends only, sorry, it depends only on the points R and P, that is initial point and the final point. Now, one more thing we have to conclude here. Equation 2 defines potential energy difference in terms of the physically meaningful quantity work. That means already, as I told you, the difference of potential energy is equal to work done. In simple words, in normal words, how you can say the difference of potential energy is equal to the amount of work done. Next, if we see what, therefore, we can define potential energy as follows. Now we come to the definition of potential energy. We come to the definition of potential energy. Potential energy of charge Q at a point in the presence of field due to any charge configuration is the work done by the external force that is equal and opposite to the electric force in bringing the charge Q from infinity to that point. This is the definition. Potential energy of charge Q at a point is the work done by the external force in bringing the charge Q from infinity to that point. In simple words, imagine the charge small q is very, very, very far away. That is called as infinity. So we are bringing it from infinity to a point, to a point where this that point, the final point, final point is in the electric field created by some other charge. That is, in this figure, capital Q has created an electric field. In that electric field, P is a point. Therefore, we are bringing small q from infinity to the point P. From infinity means we are bringing it from very far away distance to a point P into the electric field. P is in the electric field. That electric field was created by some other charge capital Q. So once again, let us have a clear definition of the potential energy. Potential energy of a charge Q at a point is the work done by the external force in bringing the charge Q from infinity to that point. So what we can say, the potential energy at, of a charge Q is equal to the amount of work done when what happens when you do the work, when you do some work to bring it from infinity to a point in the electric field, you are applying some force, therefore work is done. That work done is stored as potential energy. That work done is stored as potential energy. So this is the definition of the potential energy. So next, let us define electrostatic potential. We will go to the topic electrostatic potential. So work done by external force in bringing a unit positive charge from point R to P. A unit positive charge. So far, I was explaining about work done to bring a charge small q. all this discussion so far was about a test charge small q. Now I'm changing the words. Work done in bringing a unit positive charge. Work done in bringing a unit positive charge from infinity into the electric field. Okay, so for example, before going to the infinity, let us take the same points P and R. First, imagine we are bringing a unit positive charge. Unit positive charge means 1 coulomb charge, plus 1 coulomb charge. Plus 1 coulomb charge is nothing but unit positive charge. So we are taking plus 1 coulomb charge from the point R to the point P. Therefore, potential difference, that is potential difference between the points P and R, that is Vp minus Vr is equal to Up minus Ur divided by Q. Up minus Ur, we have seen the difference of potential energy from the previous topic. Now that is divided by Q, then it gives for 1 unit positive charge. Whenever you divide with the charge small q, that gives the result for 1 unit positive charge. Vp and Vr are the electrostatic potentials at the points P and R respectively. Therefore, work done by the external force in bringing a unit positive charge from infinity to a point is equal to electrostatic potential at that point. So, electrostatic potential, it is defined as the work done by an external force. What we are doing by the force, we are bringing 1 unit positive charge. 1 unit positive charge means plus 1 coulomb positive charge. From where to where? We are bringing from infinity to a point in the electric field. So to do this work, we are applying some external force. So this work done will be stored as potential energy. So that is called as electrostatic potential at that particular point. So electrostatic potential, capital V, it is defined as electrostatic potential at any point in a region with electrostatic field is the work done in bringing a unit positive charge from infinity to that point. Once again, I repeat, electrostatic potential at any point in a region with electrostatic field is the work done in bringing a unit positive charge from infinity to that point. So, in simple words, what I can tell you is there is a unit positive charge, that means 1 coulomb positive charge. We are bringing it from very far away distance, that is called as infinity, and we are bringing from infinity into a point, into electric field. That field was created by some other charge. We are bringing it from infinity to a point inside the electric field. For that, we are doing some work done. That work done is called as electrostatic potential. This is in the simple words. So we are bringing 1 unit positive charge from infinity to a point. That point is within the electric field created by some other charge. For that, we are doing some work. That work done is called as electrostatic potential. So that is the electrostatic potential. Now, let us derive the expression for the potential due to a point charge. So let us start our derivation. Please look at the figure. This is the derivation, potential due to a point charge. So potential due to a point charge, we have to derive the expression now. Here, if you see in this figure, as usual, like earlier what I told, capital Q is a big charge which is position at the origin, which is at the origin, and the small q is the charge which we are bringing from infinity in the earlier discussion. Now we have changed our statement. In place of small q charge, now we are taking 1 coulomb positive charge. That is called as unit positive charge. That is called as test charge. Now the test charge is 1 unit positive charge. That means plus 1 coulomb charge. We are bringing plus 1 coulomb from infinity to a point P. This point P is at a distance r bar from the origin. That means the position vector of P from the origin is r bar. So once again I define. Once again I will tell you what we are bringing 1 unit positive charge from infinity to a point P into the electrostatic field. We are bringing 1 unit positive charge from infinity to a point P into the electrostatic field. For that, we are doing some work. So let us start our derivation. Now, let us consider the point charge capital Q at the origin as shown in the figure. Already I told you. We wish to determine the potential at the point P. What we want to know? We want to find the potential at the point P with the position vector r bar from the origin. Already I told you position vector means the position of the point P from the origin is at a distance of r bar. Now, for that, we must calculate the work done in bringing a unit positive charge, that is a test charge, from infinity to the point P. So, we are bringing 1 unit positive charge from infinity to the point P. For Q greater than 0, that means if Q is a positive charge, the work done against the repulsive force on the test charge is positive. It is natural, we know. If Q is greater than 0, that means capital Q is positive. Plus 1 coulomb, it is also positive. Both positive, they repel each other. So there is a repulsive force. Therefore, we are doing some work against the repulsive force, that is the work is positive. Now we choose a path along the radial direction from infinity to the point P. You can select any path. As I told you earlier, it does not depend upon the path which we select. It depends upon the initial position and final position. But for simplicity, we have taken a straight line. The straight line that is going from the Q, so that is called as a radial direction. Radial direction. We have selected the path in the radial direction from infinity to the point P. Now, coming to the derivation, let us take the derivation in a simple manner. It is not a complicated derivation, very simple one. So before calculating the whole work done from infinity to the point P, first let us start the work done for a small distance, for a small distance. For that, I'll just give you an example. Suppose if we are traveling from Goa to Mumbai, so we are traveling by our own vehicle. Then how much petrol our car takes, we don't know. For that, first we calculate the amount of petrol for the first 10 kilometers. Depending upon that, we can calculate the amount of petrol required by our car for the full journey. That means first we calculate for a small distance and then we calculate for the whole journey. In the same way, here also, first we will calculate the work done for a small distance of delta r dash. That is, that is a point we will take in between, that is P dash on the path, and we will calculate for that small path, and then we will integrate to get the total work done. So at some intermediate point P dash on the path, the electrostatic force on a unit positive charge. So let us see, you can see in the picture, on the way from infinity to the point P, we have another point P dash. P dash is at a distance of R dash. P dash is at a distance of R dash. Therefore, force between capital Q and plus 1 coulomb, that is electrostatic force, that is Coulomb's force, that is equal to capital Q into 1 by 4 pi epsilon naught r dash square into r dash cap. Let it be equation number 1. R dash is the distance of the point P dash. That means on the way, when the plus 1 coulomb is at a distance of R dash, the force between capital Q and plus 1 coulomb we have calculated Q into 1 by 4 pi epsilon naught R dash square into R dash cap. Equation number 1. And R dash cap, as all of you know, it is the unit vector along OP dash. Work done against this force from R dash to R dash plus delta R dash. That means, as I told you, first we will calculate the work done for a small distance delta R dash. As I told you, the example of the car and the petrol, first 10 kilometers, we will calculate how much petrol we are using. And after that, we can calculate for the whole journey and we can fill the tank. In the same way, we can calculate here work done for a small distance delta R dash, and then we will integrate it to get the total work done from infinity to the point P. So work done for a small distance delta R dash, that is delta W is equal to minus Q by 4 pi epsilon naught R dash square delta R dash. Equation number 2. You may get a doubt here why I kept a negative sign here. So the negative sign appears because for delta R dash less than 0, delta W is positive. That is, the amount of work done is positive. That means we are coming towards the positive, that charge capital Q. We are coming towards the positive charge capital Q. Therefore, we have taken delta R dash less than 0. Therefore, we have kept a negative sign here. And after that, total work done W by the external force is obtained by integrating equation 2 from R dash is equal to infinity to R dash is equal to R. Now we are doing the total work done by integrating the above equation from infinity to the point P. P is at a distance of R. Therefore, we take the integration limits, that is from infinity to R. Starting point is infinity, that is very far away point, and the final point is P. P is at a distance of R from the origin. Therefore, we are integrating between infinity we are integrating between the limits infinity and R. Therefore, W is equal to minus integration of lower limit infinity, upper limit R, Q divided by 4 pi epsilon naught R dash square dr dash. So take out the constants which cannot be integrated, that is Q by 4 pi epsilon naught. You will take them out and you will get integration of dr dash by r dash square. Dr dash by r dash square. I hope you all know the integration. Integration of x to the power of n dx is equal to x to the power of n plus 1 by n plus 1. In the same way, here r dash square is in the denominator. When it goes up, it will become r dash to the power of minus 2. Then after integration, it will become r dash minus 2 plus 1 by minus 2 plus 1. Therefore, it will become minus 1 by r dash. Therefore, minus symbol will be cancelled because already there is a minus in front of the integration symbol. Now, after integration, you are getting a minus. Minus and minus will be cancelled and you will get 1 by r dash with the limits infinity and r. First, substitute the upper limit, then substitute the lower limit. And I hope you all know the integration. Q by 4 pi epsilon naught, 1 by r minus 1 by infinity. Wherever r dash is there, first you substitute the upper limit r and minus substitute the lower limit infinity. So it will become q by 4 pi epsilon naught 1 by r minus 1 by infinity. That is 1 by infinity is 0. Therefore, you will get q by 4 pi epsilon naught 1 by r. That is equal to q by 4 pi epsilon naught r. This, by definition, is the potential at P due to the charge capital Q. So, by definition means we defined, many times I have defined that it is by definition, it is nothing but the work done to bring a unit positive charge from infinity to the point P is nothing but potential at the point P. Therefore, this is the expression for the potential, that is V of R, that is potential at the point P, which is at a distance r from the origin, is equal to q by 4 pi epsilon naught r. So once again I tell, the potential at the point P is nothing but the work done in bringing a unit positive charge from infinity to the point P, which is at a distance r bar from the origin where capital Q is placed. Therefore, potential at the point P, that is V of r, is equal to Q by 4 pi epsilon naught r. Thank you for watching the video. If you have any doubts, you can contact me. Let us meet in the next video. Till then, bye.